Thank you. Thanks for the invitation. Here we are. Thanks for coming. I want to, it's a shame that we're not all in Argentina, but it's nice weather here too today. I want to talk about joint work that I did with my colleague Cosmin Pohoata, who's also at Yale, postdoc here, about a new model of random tilings. And feel free to stop me with questions along the way. My goal today is to sort of help, hopefully you will understand everything I have to say. I want to make it elementary. Let me first sort of motivate by talking about random tilings. What is the random tiling model? Why do we care about it? First of all, we're going to just, let me just make pictures. I'm going to make pictures in 2 dimensions, although for most of the talk, I'll be tiling arbitrary dimensions or arbitrary graphs. So what is the random tiling model? We have a region in for example, the plane, like this square, and we have a set of tiles, which are copies of some small set of prototiles, which are just, maybe you can think of them as polygons in the plane. Like the case illustrated here, which is just the domino tilings, right? So 2x1 rectangles. There's 2 kinds of 2x1 rectangles. We want to tile some region, and of course, this is a classical problem. But the first question, even the first question you might ask, is there a tiling with copies of the tiles? That's already quite hard, NP hard. And if you're tiling an infinite region like the whole plane, it's even undecidable. This was a famous result from the 70s by Berger. Can we, right? Question 1, right? Can we tile the region R with, let's say, translated copies of the tiles from T? And that's already hard, NP hard. Even harder question, how many ways can you tile that region? I'm not saying it's hard for every set of tiles, but in general, it's hard. In particular, for for these 2x1 rectangles, we do know how to solve these questions. And the third question, even the hardest one is, and which is the one we really care about, can we describe the structure of a large or possibly infinite random tiling? And that's the random tiling problem in a nutshell. Of course, then because these are so hard, we're going to study some very simple instances of these tiling problems. Hopefully, we can get some, get even a start on these problems. And what you find is that even the simple ones, although they're hard, in some cases we can say something non-trivial about them. Here's just some examples, by the way, of random tiling problems. Here you see the dominoes again, but instead of tiling a square, I tiled a tilted square. And you can see that it has some interesting internal structure. This is a random tiling, just uniformly random tiling. What I mean is I took all possible tilings of that region and I chose one at random. And it has some interesting internal structure that you wouldn't have guessed a priori. And same thing with these other kinds of tiles. Here's some other kinds of tiles. This one is related to the square ice model or 6-vertex model, if you know what that is. I'm not going to explain too much in detail about what these other tiling models are. I'll generalize things later. But what you see in these examples is that even though the tiles are very simple, right? They're like the simplest possible kinds of tiles you might imagine, right? These 2 rhombi, a square and a 45-degree rhombus. The structure of the random tiling has some interesting features. Right over here, right, you see near the corners that there's some different colors. The different colors correspond to different shifts of the vertical and horizontal tiles. There's something non-trivial going on here, even for the simplest kinds of tiles. And that's the kind of behavior we would like to understand. But you know, we shouldn't get our hopes up too far because of these you know, hardness issues, right? Even for a general set of tiles, even finding a tiling is an NP-hard problem. But in the cases, and let me go farther, in the cases that we have been able to analyze, like the, you know, domino case, the 2x1 and 1x2 rectangles, it turns out that there's some very interesting and beautiful deep mathematics in there. And so even though the questions are hard, in the cases we understand, they lead to some interesting mathematics, which is what we're here for, right? That you can see some sort of phase transitions, whatever that means, some conformal invariance, which you know, I don't want to explain what that means, but maybe at the end of the talk you'll see a little bit. There's a certain amount of connection with some discrete geometry, which is not at all evident ahead of time, right? There's some interesting probability theory related to, you know, SLE, CLE, quantum gravity. These are just some sort of buzzwords that happen in random tilings, and you know, we don't have to understand them to know that, you know, there's a lot of people, a lot of mathematicians who have worked on that successfully and made lots of progress on these various areas, right? You can even find some sort of aperiodicity and quasicrystals when you put these tiles together. If my tiles were Penrose tilings, as you know, Penrose tilings, they only fit together in a non-periodic fashion, right? All this kind of interesting mathematics sort of comes up in these tiling models. So what I want to do in this talk is treat a sort of cousin or an easier cousin of the random tiling model, one that you know, has some of the same features, interesting features that we care about, the exact counting, some limit shapes, some phase transitions, crystals and quasicrystals, and some conformal invariance. But in a tractable way, in a way that we can, you know, use some, you know, actually deal with in a mathematical way, in a reasonably general setting. Right, so that's the goal for today. Okay. Before I get started, I want to point out the one sort of important tool, which I think is probably familiar to everybody, but I want to remind you, it's just a tiny bit of probability that I'm going to use. And let me just illustrate it in sort of one dimension, but later on we'll do a higher dimensional version of this, which, you know, I don't know exactly what it's called, but Greg Lawler told me, or in some paper, he called it exponential tilting. But here it is. Suppose I just have a fair coin and I perform a sequence of fair coin flips, and I record the number of heads and tails in a path, right? So each head takes me to the right, in path in the plane. Each head starting the origin, each head takes me to the right, and each tail takes me up. And, you know, I flip the coin many, many times, and this path drifts off, of course, at slope 1, because my coin is fair. But now suppose that I don't want to just go anywhere. I have a particular goal in mind, which is to end up at 2n comma n. You think of n as like 100 or 1,000, whatever, right? I have a particular destination that I'm trying to get to, right? So what I can do is flip, you know, three n coins and hope that I just arrive there. And of course, that's a very small probability event. When n is large, the probability that I get exactly at that this path passes through exactly 2nn is sort of exponentially small in n. But it does happen once in a while, and I'm going to condition on the event that that happens, and then ask, what does my path look like, right? If you condition, what that means is just I ignore every possible experiment except the ones where I land exactly at 2nn, and then ask, what does the path look like? Well, if you condition on the endpoint, then the distribution of coin flips will be indistinguishable from a distribution of coin flips where I used a biased coin with bias 2/3. That is, you know, I have to, each horizontal step will be 2/3, will be twice as likely as a vertical step. So, you know, if once you fix the endpoints, the bias essentially of the coin plays no role. So I might as well have used a coin with bias 2/3 to get to that point. It would have saved me a lot of time. All right, does that make sense? Is that a familiar concept? So, right, right. So just to say it again, if I have a random walk and I have a particular destination in mind, then somehow if I choose the correct bias of the coin, I can get there much more rapidly than just using an unbiased bias situation. Okay, that was the probability tool that I'm going to use. Now let me introduce the tiling model that we're going to study. It's called the multinomial tiling model because at some point there's some multinomial coefficients, although I planned the talk so you won't actually see those multinomial coefficients in there, but they're hiding in the background. I apologize for that. Okay, so here's the setup. I have a finite graph G, right? And I'm going to take a finite set of subsets of the graph, which I'm going to call tiles. So the tiles are, you know, capital T is a set of tiles, T1 through Tk. Those are just subsets of the graph G, and those are, which I'm going to think of those as tiles. And if you like, I'm going to put a weight on each tile, which tells me how much I like that tile. For the purposes of this talk, for most of the talk, you can just assume all the weights are equal to 1. So I'm just sort of giving each tiling equal weight, right? And, you know, just to make sure we're all understanding, is suppose I want to tile some region in the plane, I can replace that region in the plane with a graph with one vertex for each square. And then maybe my tiles are, for example, translates of some set of prototiles. So this is a more general example, more general setup than the tiling a region in the plane with polygons or polyominoes, but it you know, contains that case. Now, I'm not going to tile G. First of all, I'm going to make a new graph by replacing each vertex. So first of all, I'm going to pick an integer, a positive integer for each vertex, which I'm going to think of as sort of a multiplicity at each vertex. And I'm going to make a new graph G sub n, right? So n vector is the vector of multiplicities, one for each vertex. And you should think of these n's as being some large numbers. Maybe they're all equal to each other, like 100. Okay, so G sub n is the n-fold blowup of the graph G. And what do I mean by that? Each vertex of G, you replace it with n vertices. Vertex u, you replace it with n sub u vertices. And then for each edge between two vertices of G, you replace it with a complete bipartite graph between all lifts of u and all lifts of v. So for every edge of G, you get this sort of complete bipartite graph lying over it. So here, that's what I wrote here. Gn is the graph obtained from G by replacing each vertex with nv and each edge with a complete bipartite graph. And of course, if I have a tile, which is a subset of the downstairs graph, I can lift that to a tile in many different ways, right? I'm not going to blow up the vertices of the tile. I'm just going to take the tile and I can insert it in the upper graph in many ways. And I'm going to call an n-fold tiling. It's just going to be a tiling of G sub n, the n-fold graph. Does that make sense? So I'll illustrate it in a second. But each tile is a set of vertices of G, and I can lift that in many different ways to a subset of vertices of the graph Gn, the blown up graph. And I'm going to let omega sub n be the set of n-fold tilings. So I'm really, it is just a standard tiling problem. It's just a tiling problem of this blown up graph. And there's, let's see, just to be aware, just sort of as just to be aware of the following issue. Even if your tile doesn't, it doesn't tile the original graph, it may tile the blown up graph. And here's an example, right? So let me just read the top slide. There may be n-fold tilings, even if there are no sort of one-fold tiling. A one-fold tiling is a tiling in the usual sense. If I take, for example, this tile, this little polyomino, it's a annulus. You can't tile the plane with that annulus, of course, but you can tile the 8-fold blow up of the plane or some torus, right? How do you do it? Well, suppose this is my torus here, 4x4 torus. I glue the opposite sides together by translation, the horizontal and vertical sides and the left and right sides. Then I could just take this tile and translate it to every possible location in that torus. That will cover each vertex exactly 8 times because the tile has area 8. And so then I can lift I can lift each of those copies into the lifted graph, into the blown up graph in many different ways, but there is at least one tiling of the 8-fold tiling of this torus. Even though the tile looks wonky, you wouldn't try to tile the plane with that tile. Okay, let's go on. Right, our tiles have weights, and I don't mind if you won't really lose anything if you consider all the weights to be 1, at least at the beginning. But if you do have a weight function on the tiles, then you can give a weight to a n-fold tiling, which is just the product of the weights of its tiles. So if you have an n-fold tiling, m, it has a weight w sub m, which is the product over all the prototiles of the number of w, that weight w of t, the weight of the tile, to the power, the multiplicity of that tile. And then the quantity we care about, I mean, the first counting problem we care about is this partition function, what's called the partition function z, is just the sum of the weights of all tilings, of all n-fold tilings, right? And if you want to set all the weights to be 1, this is just the total number of n-fold tilings. Okay, and let me skip down to the theorem, and then I'll define the polynomial in a second. The theorem, the first combinatorial theorem, which is really actually not very hard, is that if I make a generating function out of these partition functions, so I'm going to take the partition function, this is the sum of all weights, the weighted sum of tilings, and I multiply it by some formal, I make it into a sort of a power series by multiplying by x to the n divided by n factorial. N bar factorial is the product of the n factorials of the multiplicities. And then I sum over all possible multiplicities. This big power series actually has a very simple combinatorial form. It's just the exponent of another power series p, which is just a polynomial. It's the exponent of a certain polynomial p. And here's the polynomial. Well, the polynomial just has one term for each tile. Remember, there's a finite number of tiles downstairs, and each tile has a weight, w sub t, and I'm going to associate a variable x to every vertex of the graph G, and then for every tile, I get a monomial, which is the product of the variables of the tiles which it covers, of the vertices which it covers. So your data for a tiling is a set of prototiles, which are just subsets of the graph G. From that data, you construct this very simple polynomial, and then the exponent of that polynomial is the generating function for these partition functions. And if you restrict yourself to counting tilings where you use k total tiles, then you get a simpler expression. It's just p to the k over k factorial. That's what I wrote in red here. And I don't want to prove this theorem. It's not terribly exciting. It just involves some manipulation with some multinomial coefficients. I think you can all prove that to yourself, or you can look in the paper. I just wrote easy combinatorial. I know that's a little bit of a cop-out, but I want to get to the more interesting consequences. It's an easy result, but it has an important sort of interpretation. Let me put it that way. And here's the interpretation, which I also put in a box. If you think, right, P is a certain polynomial which has one term for each different tile, each different possible tile. What is P to the K? When you expand P to the K, right, it's like picking K different tiles, right? It's like you have a bag of prototiles. You reach into your bag, you pick a prototile, you reach into a bag, you pick another prototile. You do that K times, and then you have all your tiles and you put them on the graph. That's the sort of, and then the K factorial in the denominator means you ignore the order in which you did this. So you're really just taking an unordered subset, multi-set of K tiles. So that's what I wrote. Pick the tiles independently and then ignore the order. So I think it's time to do an example. Here's a very simple example. Hopefully this will help you catch up if you got lost. Let's just take our graph to be this 2x3 grid, well, 3x2 grid, right? It's got 6 vertices, and my set of tiles, I'm going to choose as tiles the set of all pairs of adjacent vertices, the edges. And I'm going to set all the multiplicities to be some large constant n, and all the weights to be 1, just to be simple. Okay, so then the polynomial has 7 terms, one term for each edge, 1 term for each tile. For example, the first term is x1, x4, that just means this tile here. And x1, x5 means that tile, and so on. And so the tiling problem becomes the following game, very simple game. Here's your graph. You have 1 bucket at each vertex, which is initially empty. And now you pick a pair of adjacent buckets, pick 2 adjacent buckets, and you put 1 ball into each bucket. That corresponds to adding that particular tile into the graph. And then you repeat. You do this, 3n times, where n is the multiplicity, and then so as you repeat this, the buckets slowly get filled up, and you hope at the end of the day, your experiment is a success. After you've put in 3n tiles, you filled every bucket exactly to the top with height n. So you put 1 ball in each. That's great. So each placing a tile means to just take 2 adjacent buckets and put 1 ball in each, and you repeat until each bucket has exactly n balls. And of course, this is kind of unlikely to happen. So if it doesn't work, you just empty the buckets and start over, and you do it over and over again until it happens. It will eventually happen, possibly with some exponentially small probability, but it will happen, and then that's your tiling. That gives you your tiling. And of course, you can see that this is a version of that random walk problem. It's a random walk in some 6-dimensional space, the space defined by the buckets, by the how much each bucket is filled, and in Z6 plus, right? You start at the origin where all the buckets are empty, and then each tile you increase 2 of the coordinates in Z6, and sorry, I just saw.
Sorry, Richard, there is a question in the chat. Andrew, you can unmute yourself if you want to.
I apologize, that's my mistake. Yeah, the numbering is not important for the moment. But yeah, either numbering works, I think. But okay, you're right, the polynomial is slightly different.
Are they meant to be the same?
What? They're meant to be the same. Yeah. They're meant to be the same. That's my mistake. Sorry? Okay. If we, so here's the problem, right? We have 7 tiles, and if we pick each tile with probability 1/7, it's very unlikely that we will fill all the buckets up to size 100 at the same time, right? Because if we pick each edge at random with probably 1/7, buckets 2 and 5 are going to fill up more quickly than the others, just because they have 3 edges adjacent to them, right? They fill up at rate 3/7, and these fill up at rate 2/7. And that's right. So we're trying to make this random walk, which ends at a particular location, but it's heading off in the wrong direction. So we're going to have to change the bias. I mean, we would like to change the bias so that it heads in the correct direction, and that's what we need to do. We need to do this exponential tilting, like I talked about at the beginning. But we're going to bias the walk by giving buckets 1, 3, 4, and 6, the buckets on the outside, a higher weight. We're going to change the probability distribution. Instead of using just the uniform distribution on tiles, we're going to change the distribution. And how do we change it? Well, we're going to bias it by weighting the buckets. Each bucket is now going to get a weight, x1 through x6, a positive real number. And then the probability of a tile is going to be the product of the weights of its buckets. I mean, proportional to the product of the weights of its buckets. So, and what we would like is to adjust those rates so that all the buckets are being filled up at the same rate. So the rate of bucket 1 is now going to be, well, it's going to be, if the new weights of the buckets are x1 through x6, the rate of bucket 1 is x1, x4 plus x1, x2, right? Because bucket 1 gets contributed by this edge or from that edge. And divided by p, the p is the normalization factor for this new distribution. Okay, so we need to, in order to, make things work out, to fill the buckets at the same rate, we have to solve this sort of nonlinear system of equations for the xi's, right? You see that for each bucket, there's 6 equations here, and there's 6 variables. In principle, we can solve those, and yes, well, of course, that was just the example. In general, we need to do the same thing, right? We need to solve a certain system of equations where we have one variable for each bucket, that is one variable for each edge, for each vertex in our graph. And this is the equation, right? The certain derivative, the xv derivative of p divided by p times xv equals this quantity alpha, which is the desired rate that the bucket gets filled. And the theorem, as you might expect, is that there is a solution, right? As long as the rates are feasible, that is, there exists a tiling which has those rates. I didn't define feasible, but I'm trying to define it now, right? Not all tiles have, it may be that your tiling problem is just, unsolvable. I mean, not unsolvable, but has no solutions. But if it does have a solution, then that's what I mean by feasibility. If the rates are feasible, then there is an essentially unique solution to this system of equations. And by essentially unique, I mean, well, it's not unique, but it leads to a unique, weight function on the tiles. So even though the solution to this system of equations may not be unique, every solution gives you the same weight function on the tiles, on the actual tiles themselves. So there's a unique probability distribution on the tiles, which is gauge equivalent to the original one, and has the desired property. The desired property, I just repeated it here, the sum of the weights, the new weights of the tiles over all tiles which contain any particular vertex, the sum over tiles containing vertex V is the desired rate for V. I'm sorry, there's a lot of notation there, but hopefully you can see what's going on. And once we have that special distribution, the gauge equivalent, the critical, the one that satisfies the equations, then it's easy to compute the sort of growth rate of the number of solutions, the number of tilings. It's just some combinatorial, the exponential growth rate of the partition function, ZWN, can be computed. You just remove the appropriate factorials, and then, here it is. It's not so important what it is, but you can, once you've solved those polynomial equations, which, a priori looks kind of tough, but I mean, one can show that you can get these by maximizing a certain convex function. Okay, and yeah, just for the sake of going back to our example, we had our example with our 6 buckets. If I change the weights of the buckets by putting the ones on the outside to be the golden ratio and the ones on the inside to be 1, then everything works out beautifully. The blue numbers on the edges are the probability that we're supposed to choose that particular edge. And you can see that the sum of the probabilities of, well, this edge and this edge, they add up to, hopefully, if I did it right, they add up to 1/3, the correct rate. And yeah, the growth rate is some number like that. Okay, does that make sense? Any questions? I was told to pause halfway through to ask for questions, so here I am.
Okay, just go, please.
Okay, good. Okay, thanks, Pablo. All right, so now we have everything everything set up. You can ask the next question, which is, if I take a random tiling, what does it look like? I mean, how do I describe a random tiling? And of course, the natural random variable is how many times do we use each tile, right? How many times do we place each tile, right? Typically, that's a random number, right? And well, as you know, we are, but now it's kind of a standard random walk problem, right? We've got a bag of tiles. It has some interesting distribution, which is no longer uniform, but you know, we pull we do k times the following experiment, reach into our bag of tiles, pull one out with respect to that probability distribution. So each tile is just going to be used a binomial number of times, binomial distribution, and with a certain mean, which is given by k, the number of tiles, times that its probability, you know, which is the critical weight function. And of course, for large k, this tends to a Gaussian random variable. So we're in an excellent setting where our random variables turn out to be Gaussian, at least in the large n limit, when the multiplicities get large. Of course, you know, it's not exactly as easy as I said, because we can't just do the experiment k times and then stop. At the end of the day, we have to condition. We have that conditioning. We want to make sure all of our buckets are filled up at the same level. But then, so that what it means is we take our Gaussian random variable and we have to condition the Gaussian to lie in a certain subspace. And the subspace is defined by the multiplicity condition. It's a linear subspace. But the nice thing is, if you have this multidimensional Gaussian random variable, this multidimensional bell curve, and you condition it to lie on a certain linear subspace, the conditioned random variable is also Gaussian. So in some sense, we win because of this nice restriction property of Gaussian random variables. And so that's the next theorem. So XTs are the number of times we use tile T in this experiment. We subtract the mean value, and I'm just going to normalize by dividing by the square root of the number of tiles. And let's call this this is like the fluctuation around the mean value of that random variable. And this thing converges to a certain multidimensional Gaussian random variable. And because everything is sort of linear, we can write down an explicit formula for the covariance of that random variable. A multidimensional Gaussian random variable is defined by its, the quadratic form in the exponent of the density, or if you like, the inverse of that quadratic form is the covariance. So this function, the covariance between pairs of tiles, that defines uniquely this distribution on all the tiles. And the covariance has this nice form. Well, I wrote it out here, but it's really just, well, the weight function times a certain projection, a projection matrix. Now this is just this covariance it's a matrix, right? Indexed by all the tiles. It's like a T by T matrix, where T is the number of tiles. And that matrix is a projection matrix. And what its projection is, it's a projection onto the kernel of a certain operator D, which I have to tell you about. I haven't told you about that operator D yet. And there's also a Laplacian here. What are these operators? Well, D is the very simple operator which tells you which is just the incidence matrix between tiles and vertices, right? So if you want to think of it as an operator, it's a linear map from the space of linear combinations of tiles to the linear combinations of vertices. Or if you think of it just as a matrix, it's got entries 1 and 0, and the entry 1, if the, right, so it has columns indexing tiles and rows indexing vertices, and the entry is 1 if the vertex is in the tile and 0 otherwise. Just the incidence between tiles and vertices. And of course, and there's also this Laplacian operator, which is not the standard graph Laplacian. It's a different Laplacian, but it's just d star. And I stuck inside there the diagonal matrix of weight functions. It's another linear operator on the space of vertices, on the space of functions on the vertices. Kind of like this, it's a positive, semi-definite linear map. It's not, I use the Laplacian notation. It's not the standard Laplacian, it's some tiling Laplacian. And if you want an actual formula for the entries, if you think of it as a matrix, the UV entry is just the sum of the weights of tiles which contain both vertices U and V. Okay, anyway, those are just two very simple matrices you associate to this setting. And the theorem is that the covariance is just the projection matrix onto the kernel of D along, well, I didn't tell you what it's along, but it's along the image of D star. Anyway, it's just some linear algebra which tells you everything, right? A little bit of linear algebra. And so now we can do some examples. Let's do some very simple examples, and then we'll build up in complexity to some more interesting examples. So one of the most simplest examples we thought of was, let's tile a ring, Z mod NZ, as n cycle, with translates of a tile which consists of just 3 consecutive vertices, right? So if you like, think of a ring of buckets, and then each tile consists of, I mean, you throw a ball into a bucket and the 2 adjacent buckets at the same time, and then you have to fill all the buckets up to size n. And of course, the number of times you use the tile at I, well, of course, the tile multiplicities, xi, they have to satisfy some linear equation, right? Because the bucket at I has to be filled up to level n, and it only gets contributions from xi minus 1, xi, and xi plus 1. The tiles at I minus 1, or the tiles at I, or the tiles at I plus 1. Those are the only tiles which contribute to the bucket at I. And so that gives you a linear constraint on these random variables, right? These random variables, the xi's have this linear constraint, and that linear constraint, of course, implies that xi equals xi plus 3, right? Because if you just subtract this equation from the shift, you get this equation here. All the multiplicities here are the same. And so now there's 2 cases to consider, and you know, I agree this is trivial, but it's worth going through it. If the ring has a circumference which is not a multiple of 3, then this set of linear equations is linearly independent, and there's a unique solution, which is to set all the x's to be n over 3, right? So in fact, there's no randomness left. You have to use each tile exactly n over 3 times, and the covariance matrix is just 0. On the other hand, if the ring has a circumference which is a multiple of 3, then you get something non-trivial left over. The system of equations doesn't determine all the multiplicities. There's still a rank 2 system left over, and you have to do a little work, but you eventually get the covariance matrix to be this nice sort of 3 periodic matrix here. Okay, I don't know if that was useful or not, but at least what I'm trying to illustrate is that you can solve the problem just using some linear algebra. And the next, you may complain about this example that the boundary conditions are sort of enforcing this periodicity because the constraint is so strong. So the next example is an example where we can sort of weaken that constraint by adding some errors. And so what we're going to do is tile with bars of length 3. We're going to still tile the same set, the ring of length n, but we're going to have bars of length 3 and a small density of singleton tiles, which you can think of as just sort of errors or singleton tiles, I don't know. And so we're going to let epsilon be the fraction of singleton tiles, and let's suppose that epsilon is very small. And anything very small, we can certainly do the linear algebra. It's a little bit more convenient if epsilon is not too small because the answer will change. But then you work out the linear algebra, and the circular symmetry allows you to do some Fourier transform, and the covariance function works out to be the following expression. And well, if I'm interested in the covariance between a tile at the origin here at some location and another location which is S away from it, right? I want to know what's the probability that both these tiles are there. I mean, or the covariance between the number of tiles here and the number of tiles there, right? This turns out to be just the Fourier coefficient, the Sth Fourier coefficient of a certain rational function, which is 1 over epsilon plus 1 plus z squared. That's the sort of the characteristic polynomial of the tile. And then the same thing with the z bar, 1 plus z inverse plus z to the minus 2. And then you have to sum that over all nth roots of unity, little nth roots of unity, except for the 1. Again, there's a little bit of details. There's a little bit of linear algebra, which I don't want to spend time on, and then divide by n. So there's an explicit expression for the covariance function, and you can work it out sort of asymptotically as little n gets large, and you see kind of a nice expression. There's some exponential decay in S when the tiles get far apart. There's some exponential decay, but only with the rate square root of epsilon. And then there's this sort of periodic behavior that we already saw in the previous case. So even in this sort of mollified case, when you allow some errors, you still see the tiles feeling the 3 periodicity when epsilon is small in this sort of cosine 2 pi s over 3 term. Okay, so let's now, if we go up 1 dimension, then suddenly it becomes a lot more interesting. So let's tile, rather than tiling just a ring, we're going to tile a region in the plane. And in fact, for simplicity, let's talk about either the whole plane or just some torus here. Later on, if I have time, I'll do the next case. And okay, so let's just take the simplest tile you might think of. The 2-dimensional tile is the L triomino. It's just a union of 3 squares. And we're going to take translates of that, but we'll also add, just for the sake of, so we can ignore the boundary conditions, we're going to add a small density of monomers. So 1 by 1 squares, or epsilon density of monomers. And then the covariance function has this, then we're going to, we should do it on a finite graph, but then we're going to sort of take the limit as the graph gets large, and then the sum, which we had before, becomes an integral. The upshot is that the covariance function between 2 tiles, one located at the origin and one located at S comma t, is again given by the Fourier coefficients of a certain nice rational function. And the rational function in the denominator has this characteristic function of the tile, 1 plus z plus u times 1 plus 1 over z plus 1 over u, plus the epsilon for the monomer. And why is, I mean, what's the key thing to notice here is that this denominator, when epsilon is small, this denominator blows up. I mean, the denominator goes to 0 at some point in, or goes to very close to 0 at some point along on the integral surface, on the surface of integration. And so the asymptotics is a little bit non-trivial here. You get some Bessel function. Well, here's the sort of asymptotics of this when epsilon is small. You get, first of all, you get the nice periodic behavior, the cosine 2 pi over 3 times s minus t. And then you get this Bessel function, which is one of these functions which decays as s and t gets large and blows up like a log epsilon near the origin. Okay, so here's the picture that goes with it. You imagine we're tiling a large region in the plane or a large torus with these L triominoes, and epsilon is very small. Here, epsilon was 0.001. And I'm interested in the covariance between the number of tiles at the origin and the number of tiles at some other location far away. And here the orange means positive covariance, and blue means negative, dark blue means strong negative covariance, and white means 0 covariance. So what you can see is that once you put a tile at the origin, there's this sort of sublattice where the tiles you're more likely to find tiles along this sublattice, which corresponds to the sublattice where the tiles make a nice densely packed pattern with that tile at the origin. And in fact, in the limit as epsilon goes to 0, this covariance function looks more and more like this perfect crystal, where once you put a tile at the origin, the tiles like to be along the same index 3 sublattice to make a nice tiling. But of course, for positive epsilon, there's some decay away from this perfect crystal structure. But the interesting thing is that even though the multiplicity here has gotten very large, you still detect, even if I put just one tile in, I can still detect that crystal structure. All right. And of course, there's a general theorem about what happens if I start with a polyomino and a small density of monomers. The covariance has an explicit form, which is very similar to the one you just saw. And well, the interesting thing, if you have any familiarity with Fourier series, there's something interesting going on, because sometimes the denominator gets very small. The behavior of this function depends on the zeros of this polynomial p on the unit torus. And here we are. So now, for various types of tiles, the leading asymptotics of this covariance function will behave in quite different ways depending on the type of zeros of the denominator in that covariance function, which is this characteristic polynomial. What is the characteristic polynomial? It's just the sum over all the vertices of the tile. Here we're in Z2, z to the I times w to the j. For example, for the L polyomino, the characteristic polynomial is 1 plus z plus w. This one happens to have only simple zeros on the unit torus, by which I mean they're isolated, and the zero set, the first derivatives are non-zero. On the other hand, if I take my tile to be a square, the 2 by 2 square, this has a whole line of zeros on the unit torus, and then for other tiles you get even more weird behavior. This particular tile has a whole curve of zeros on the unit torus, and I need to show you the pictures corresponding to the covariance function, right? This tile here has no zeros on the torus. This one has simple zeros, but they have irrational arguments. So those are the 5 which I want to just highlight since my time is running out. If I take a square tile, for example, so remember that I'm taking a square tile and I also have some monomers with small density. And then if the density is small, there's this nice, right? The covariance function has this decay, but the decay is kind of interesting. You see the it has this sort of interesting periodicity behavior, right? All the sort of even squares have positive covariance with respect to this center, and the odd squares have a negative covariance. And in the limit as epsilon goes to 0, the covariance function looks more and more like this sort of checkerboard pattern here. Right, here's sort of the leading asymptotics of the covariance function has this sort of -1 to the, has this sort of checkerboard behavior times this epsilon, square root of epsilon log epsilon. On the other hand, a tile like this plus polyomino, right, that's, you know, doesn't seem, you know, a priori to be significantly different than the square polyomino, but it has a much more rich and complicated covariance structure, which you know, what does this graph mean? You know, again, the orange means positive covariance, blue means negative covariance, and you know, it's a scale where the orange is the maximum, dark blue is the minimum, and you know, this picture is obtained from some Fourier coefficients of some rational function, and the covariance, but the covariance has this interesting, you know, decay. Well, it's of order 1 over epsilon squared times s squared plus t squared is 1/4, but then there's some periodic, not periodic, but some complicated prefactor, which I don't want to write down, involving some elliptic function, right? And you know, then just for fun, we looked around for a while to find a polyomino which had the property that when you look at its covariance function, it becomes a quasi-periodic. It has a quasi-periodic covariance function, right? The covariance is this, the leading term is log epsilon times this cosine, where the angles here are irrationally related to each other, which means that the tiling is sort of quasi-crystalline, right? It doesn't have any sort of long-range periodic behavior, unlike the previous example, well, maybe not that example, but right, this example here was sort of periodic. That, and the previous example was also sort of periodic. This one is a quasi-crystal, a sort of a random quasi-crystal. If I take a random tiling with this copies of this key polyomino, it will have this slightly mysterious non-periodicity. I have one more subject to talk about, but I'm slowly running out of time. Maybe I can stop and ask for questions just for brief. Any questions yet? Okay. Okay, so to sort of summarize, we start with a set of tiles. We showed that it was Gaussian, the random variable, the number of times use each tile. And then just using some linear algebra, some slightly non-trivial linear algebra, you can compute the covariance function, and it has this interesting behavior. There's another sort of limit to this setting where I'm going to tile a domain in the plane. And I want to explain where this sort of conformal invariance comes from. You know, and let me just stick with this first tile again, the L polyomino just consists of these 3 squares. And again, all the weights are 1 and all the multiplicities are n, just some large number n. We're supposed to think of capital N as being very large compared to all the other variables, all the other quantities. And I'm going to take a nice Jordan domain, U, and I'm going to approximate it with my lattice. So U delta is a delta approximation to some smooth Jordan domain in the plane. And I want to tile U delta with translates of this tile, you know, shrunken translates of that tile. And I'm interested in the set in what happens to the tiling when delta gets small. So my graph is getting finer, my mesh is getting finer and finer, and I want to describe the covariance function in that limit. And you know, there's some, we don't really need to talk too much about the boundary conditions. I'm going to take some sort of free boundary conditions where I don't control I allow the tiles to overlap the boundary, but I don't control their multiplicity there. And so the problem is the following. We need to compute this covariance function. And so that is the projection onto the kernel of this linear operator, as we saw, D. And what happens to this kernel? This kernel consists of a certain space of functions on the lattice. And in the limit, as the lattice spacing goes to 0, that kernel will converge to some continuous space of functions. And so, it's a little bit of an analysis problem now. And the appropriate thing to do for this particular tile is, first of all, apply a linear coordinate change. So rather than tile with the sort of the L shape, I'm going to tilt it over so that the tile becomes a 3 vertices of an equilateral triangle, like that. And so then this is the sort of the correct coordinate system where you start to see analytic functions. And so here's the sort of idea in a nutshell, and I apologize, this is going to go too fast, but the kernel of the operator, which we care about, a function in the kernel can be written in the following way. Every function is the real part of omega to the x minus y. So omega is just the cube root of unity, primitive cube root of unity, times some function capital F, where capital F is a quote unquote discrete analytic function. That's the idea. And I sort of try to indicate why that might be true. Let's assume that F is smooth here. Capital F is smooth. If I just apply D to such an operator, if I apply D to this expression, I get F of xy, F of x plus delta, right? D is like the incidence operator, so it tells me which vertices are adjacent with respect to the tile. And there's three, it's like a difference operator with some coefficients. And when you write it in the right coordinates, this difference operator looks exactly like the D bar derivative, Fu plus I Fv, where U and V are the horizontal and vertical, the new horizontal and vertical coordinates. Okay, so if you're in the kernel of D, then capital F should be some version of analytic. And so let me just state the result and then I'll stop. For this particular tile, the covariance function in the limit as epsilon goes to 0 gets closer and closer to a particular function, which is a sort of conformally invariant function, right? This capital B, which is the Bergman kernel. The Bergman kernel is the function which defines the projection from L2 functions to L2 holomorphic functions on U. If you haven't seen it before, it's not. It's the kernel of a certain function. It's a function which is analytic in Z and anti-analytic in Z2. And if my region happens to be the unit disk, then it has this nice simple form. Okay, and so there's an explicit sort of limit for the covariance function, and because on the disk you can actually simulate. I don't mean simulate. Give an explicit expression for the corresponding Gaussian random variable. Oh, sorry, here, right? So here's my unit disk, and what you can see is that there's this random function, random harmonic function, which looks friendly in the center, and then as you move to the boundary, it fluctuates more and more wildly. And this function is the density fluctuations of tiles on one of the 3 sublattices when delta is very small. What is that Bergman Gaussian? You just take a random analytic function. That is, you take z to the j, multiply and make the coefficients just IID standard complex normals, and sum them up, j going from 1 to infinity, take the real part. That's sort of a random harmonic function on the disk in L2. Okay, that's all. Thank you.
Okay, thank you, Richard. Please feel free to unmute yourself to ask questions. Brina, yes. Okay, yeah. Or you can also use the chat if there is any question. Okay. I think I will stop recording.